just 50 meg total for everybody to use, to share. But this sector shares is 50 on its own, this sector 50 on its own, this sector 50 on its own.
This is just by changing the base station?
Yeah, by tripling it. So before we had just one base station with one antenna on it. Now we said, okay, let's add 2 more base stations and get rid of that first antenna. So I'm going to add a base station to serve just you guys, you 3 guys, because you guys are very demanding. So I'm going to give you guys your own sector. Give you your own AP, and you 3 guys talk through him. Then I'm going to look to this area. And I'm going to say, who's here? Okay, I've got 2 guys so far in here. I'm going to give you your own sector, so that you guys don't contend with them for your bandwidth. And then I'm going to look to this area and say, okay, this other 120 degrees, you guys are on your own. I'm going to give you your own base station, so you don't have to share with these guys, because all of you guys are very demanding. Everybody wants video and everything else. So I broke it up into three base stations with 3 different antennas. And the way...
Okay, so if I'm sorry, John.
Hold on, please.
If someone comes to us and say, okay, I have this, I deployed this network, and I'm having issues, what is your suggestion? You would say, okay, change your base station, get another base station, and you have to change your antenna.
Yeah, so it depends on what. So it's a very good question.
I'm sorry, we're trying.
No, please. No, very good question. So, and this, by the way, this is not a mesh network yet. We're just talking about just general hub and spoke type of networks, for sort of hub and spoke. But so what we're talking about here is trying to resolve a capacity problem. So you, as the network engineer, first would get some feedback from the guys handling the phones. They say, hey man, there's a lot of guys calling. They said their video is not going through. They said their voice quality is really bad. They're doing speed tests. Somebody made these guys smart, and they got access to this cool tool called speed test, and they're running speed test all day long, and they're seeing, I sold them a package for 3 meg and they're only getting 100K. Sometimes they get nothing. Sometimes they get 6 meg. Sometimes they get 4 meg. Sometimes they get 1. But it's almost never better than 3 meg, and you know they're complaining. So the first thing they'll do is you'll log into the network from underneath the AP. You'll log into the network and say, okay, well, how many users are under this guy? Oh, there's 60 users. I told them not to put more than 20. They ain't 60 users, okay. So what am I supposed to do? So you start looking 60 users, and you come to the conclusion quickly that, hey, this is a capacity problem. You've determined that it's a capacity problem. You've gone through some other high-level and then deep type of analysis. But with 60, it's pretty clear, especially if your AP can only handle, let's say, 35 meg or 30 meg with a mixed environment. We'll talk about environments in a minute, inshallah. But if you started from that point and you determined you knew it was a capacity problem, then you got to revisit the layout of the network in the physical sense, knowing like where your users are. Where are they in the whole network? Can you split it up into sectors this way into 120 degree sectors, or do I have to point? Or if you had a really bad problem, you would say you would have most of your users would be in this area, and they're the ones consuming most of your capacity, and then you might need to put 2 APs pointing in the same direction. You might have to put 2 of them in the same direction to address capacity if the capacity problem is only in this area. You might run into a problem where, you get your users are in a valley. You might have a mountain here, and then your users are all down here, in this area. And it might be a city. You might be like in Salt Lake City, or you might be, just west of downtown, Chicago, for example. If somebody wanted to do wireless just west of downtown, there's nobody across the lake on the east side, right? Yes.
Yeah. Let me add one thing, if
Please.
you don't mind. When you were talking about capacity, coverage, total bandwidth, latency, frequency, availability, we didn't mention anything about if there is a mountain, trees, lakes. What would you put the under?
Yes, remind me just in another minute, as soon as we do this one,
okay.
We'll come to it, inshallah. So, the 2 things you start looking at when you're looking at the topography of the land, like the brother's talking about. But let's assume that you were trying to serve just this area here. And so you're looking for 180 degree coverage. You're looking to serve those guys here. Always, as a rule of thumb, if you're the guy who wants to make yourself not worry about interference, the narrower your antenna is, the better.
Oh boy.
As a rule of thumb. The narrower the antenna is, the better. If you're trying to minimize interference that you would hear from different directions. If you're just worried about coverage and ease of how do I get as many users on here without the ghalib hali, putting together different APs and different antennas, you'll use an Omni because you want to hear everybody equally. So the reason why the more narrow, the more directional an antenna is, the better, is for the same reasons that they put on a horse, you know, those blinders, you know, they put those blinders on a horse, so that he doesn't see stuff that can scare him on the side, so it doesn't interfere with his, you know, ability to go forward and not worry about what's going on. But if he can see everything on the sides and hear everything from what's going on, he'll jump every time he sees any kind of movement anywhere. But they put those blinders so he's not startled by people. And the same sort of thing with an antenna. If I only want to talk to you three guys, then I want to minimize the problems that I might hear from these guys, even though I'll put them on a different frequency. But still, if I keep myself completely open and put my guard completely down, I can hear some people from here, I can hear some people from there. Somebody might put up a new network on the same frequency 5 miles down that way who's not part of my network. He belongs to somebody else, some other network, because this is unlicensed space. People will do whatever they want. He wants to start up his own business. I'll start up my own business too. He'll start serving his 10 users and start increasing his network, and his frequency will bleed right into you. And the more you can point to...
Don't they use a different channel?
They can, but let's say they run out.
Oh.
And he wants to start his business.
Yeah,
he noticed
it's unlicensed.
somebody else, it's unlicensed. They can do what they want. Usually what happens in these spectrum wars, in the unlicensed band, it's usually the bigger guy wins. Because he has more customers, and he can put up more towers, he can move things. The new guy is going to be kind of limited. So he'll eventually go away, but he'll be a pest to the big guy because he has a lot of users on his network, and he doesn't want to be, you know, worried about his users getting unhappy and leaving and going somewhere else. So to minimize the impact from this is the trade-off you make. The trade-off you make is if you want to have less possibilities for interference from outside, you make your antenna narrow so that it doesn't hear stuff from over there. I want to point only and talk to you guys. But on the negative side, if some new user you want to add is not in this area, you'd have to add a new AP to cover him with a new antenna totally on this side. Even though maybe he would have fit in here because you're not over capacity yet, but your antenna can't see him because now he's slightly outside of that area, right? And so if you had a problem like this where you're trying to cover an area and it's just people, you don't care, there's nobody behind you because it's a big mountain and on the other side is a big lake, there's nobody there. So you just want to cover this area. You might say, okay, I'm going to find an antenna that's as close to 180 degree as possible. What does 180 degree antenna mean? It means that he can serve everybody in the front, and in the back, it doesn't serve much. There's nothing that's perfect, which gives you absolutely no power in the back, but a 180 degree antenna focuses the energy in the front and puts out most of the power in the front and very little in the back. And we'll talk about antenna patterns here in a second. So that's what you would do in this area, and you can serve them with one AP. But what if it wasn't enough? You ran out of capacity. And you're serving just one area, and you can't do it by saying this is 60 degrees here and this is 60 degrees here. You can find antennas for any kind of degree you want, mostly. But some of the standard ones, 45 degree sectors, 60 degree sectors, 90 degree sectors, 120 degree sectors. There's 180, and then there's the omnis. And then after that, it's your own prowess in terms of how you set up. You can put multiple antennas together and create your own sectors, but when you combine externally on your own, there's combiner loss and things that you have to worry about, which is not ideal. So, if we talk, before we go to your question, I think, just to cover one other thing, and I'm sorry it's going to be kind of, so,
the better
let's talk about antenna patterns a little bit. So when you decide you want to deploy, and you've already said, I'm going to cut this up into 3 sectors. I'm going to use 3 sectors, and I want these guys to be facing, different directions, 120, 120, 120. So how do you go about understanding what the vendor is going to give you for an antenna? You're going to buy your antenna from somewhere else. You're not going to create your own antenna. It's a specialty that takes years of expertise. And so the antenna vendor will tell you, here is what the radiation pattern looks like. Looks like a Pac-Man thing, right? That is Pac-Man. So looking at this thing, you know, it'll have multiple circles around it. Should have drawn those in different colors. So I'll draw it now without the pieces, and I'll show you what I'm talking about. So if your antenna pattern is like this, it looks something like this. This says, and if this is the front of the antenna, and this is 360 degrees all the way around, so this will be the degrees. So this will be like 90. Oh, sorry, 90 minus 90, and this is like the 180 from the 0. So if you're looking right in front of the antenna, that's where the peak gain is. Most of the power will be, because an antenna actually, if it's a passive antenna, remember, you can't have gain, real gain, from nothing, right? Everything has to come from somewhere. But where does an antenna get its quote-unquote gain from, right? They're all passive devices. If you guys remember, if you want gain, you use an amplifier, right? You use a power amplifier, and it costs you power. You have to feed it DC power, and it converts that DC, and when your RF signal comes in, it raises its peak-to-peak level. So now suddenly you have something that's raised by the rail of the voltage that you put in, and however that amplifier is designed with how many stages in it, you get some gain. So how do you get gain from passive elements? Yeah, these are passive elements. There's just microstrip lines or little elements pointing in different directions. How do you get gain? Do you really get gain? So what it is, if you can imagine yourself having a balloon. If then affected the balloon and you put some, you just blew up your balloon and you had some air in it, it takes a certain shape. So with a certain shape, let's say kind of like the Omni, it's equally pointing in each direction. Maybe it has no gain, zero gain, but it's better than having negative, by having a lot of loss. Because normally, like if I, let's say you had your phone. Your phone has how many wireless interfaces? You got your GPS. It has an antenna for GPS, and the GPS is at about 1.5 gigahertz. It's got your Wi-Fi, which is the 5 or the 2.4 that they put in phones these days. I don't know if they put both. Both. So you got the dual mode, 2, 4, and 5 in there. Each one needs its own antenna. And then you have your cellular, and then you've got your data if you're using LTE or whatever you're using for LTE. So you could have up to 4 antennas, maybe more antennas, depending on what else is going to be put in there. So each one of those is going to have the ability to pick up energy. The ability to pick up energy. So if you start with something that doesn't have an antenna on it, you've designed a lot of RF circuits in the past, right? I mean, you put an RF circuit on the table. Even if you don't have an antenna on it, it'll pick up interference of the board itself, the components. The inductors will pick up interference. The traces, depending on how long the traces, the microstrip lines are on the board, they'll pick up energy. But the thing is, they don't pick it up at the same level that it arrives. Let's say the power arrives from me to your phone at minus 70 dBm, and we'll talk about what 70 dBm is later. It arrives at minus 70 dBm, but the radio's ability to pick up minus 70 is really bad because he doesn't have something that's efficient at picking up RF energy. So he might hear it at minus 100, 30 dB down. But if he has an antenna that's, it's efficient at picking up, but it has no gain, it might pick it up at minus 70. But if someone took a balloon, that balloon that just is good at picking up the energy, it senses any kind of air pressure that comes along on it. He's very sensitive like that. But so he can sense it. Whatever air pressure comes in, he senses the air pressure as it comes in. Very, very good at it. But then there's another device where I squeeze the balloon in one side, so that he's very, very pressurized on the one side. I squeeze them. I wish I had a balloon. I squeeze them, so that, most of the shape, Bezman Kudam, is like, sticking out from the front like this. You know what I mean? So it sticks out from the front. So suddenly now he's very sensitive. He is 10 dB more sensitive, 100 times more sensitive than he used to be to sense any kind of motion. It's real similar to that analogy. So an antenna, going back to the analogy of the antennas in our phone, because they're so small, they don't have much gain to them, but now they have efficiency, what we call efficiency, the ability to convert. If he hears minus 70, he hears minus 70. But these big antennas, we make them big. What we're doing is we're making them very directive. We're making them very directive. That means we're forcing the balloon to push the gain, to create what's gain, to take what power would have come from all the other sides, I don't want to hear it, and push that ability in the front to make the front more sensitive. And so now it becomes 10 dB more sensitive. 10 dB corresponds to 100. To a factor of 10. 20 dB would be a factor of 100. 100 times more sensitive. So if something becomes 10 times more sensitive, it's 10 dB more gain that it has the ability to send. So if I send it minus 73, he thinks he heard minus 63. He heard something 10 dB higher, because the antenna gain is now the directivity gain, which is interpreted as gain, is 10 dB better now. So when someone wants to sell you an antenna, you'll ask him to look at the antenna pattern, and the first one he'll show you is what's called the azimuth antenna pattern. The azimuth. The azimuth, when if I'm looking at my users this way, it's how much power do they see, how much. So like if I'm 120 degree antenna, I'll be like this. The people who are right in the front, if the antenna was designed right, and it's really 120 degree sector, when I aim it in the middle, Sammy will get the most power. And then as the people start getting deployed further along, so you might be 15 degrees off from center, so the power might drop a half a dB by you. By the time I get to 60 degrees on either side, the power will typically drop what we say is 3 dB. Half the power is lost. Half the gain is down. So maybe here I'll have 10 dB of gain. By the time someone is on the side over there at the edge of the sector talking to me, his power might be down by 3 dB. 3 dB corresponds to the same as half the power is, half the gain is gone. So here maybe
even though he's getting 7 dB,
he's getting
or 5.
His gain is only 7. Yeah.
7. Okay. 7.
Yeah, so,
it's.
Yeah. So if we started with 10 dB of gain at the center, right here at the center. So if this is a 120 degree antenna, that means 60 degrees on each side, right? So there's 60 degrees this way, 60 degrees that way, and the azimuth means left and right, just going left and right. So 60 degrees off. So if the gain was 10 dB here, it'll be 7 dB here. It'll be 7 dB here. That's what we call the 3 dB points. 3 dB means half. Why does 3 dB mean half? Because if you were to take 10 times the log of a half, you get minus 3. Right? If you take, because logs, what are logs? Logs are just converting linear terms to logarithmic terms, right? And so when you take something and you half it, let's say you started with something that was 100, and you divided it by 50, you cut it in half. Every time you do this 10 times the log of this, you'll always get minus 3. So something that is half as big as it used to be, it'll be down 3 dB. If something is twice as big as it used to be, it'll be 3